Welcome learners. This is Dr. T. Gangaram, lecturer in statistics, SVA Government College, Srikalahasti. Let us derive the important theorem on numerical analysis, Unit 1, fundamental theorem on finite differences. Let us look at the statement first. If f of x is a polynomial of nth degree, then the nth order difference is constant, that is delta power n f of x is equal to constant, and the higher order differences, that is delta power n plus 1 f of x must be equal to 0. In other words, delta power r f of x is equal to 0 for all r greater than or equal greater than n. If r is equal to n, delta power r f of x must be a constant. Let us look at the proof. We know that the polynomial of nth degree is written as f of x is equal to a0 plus a1x plus a2x square, so on an x power n. By definition of first forward difference, delta f of x is equal to f of x plus h minus f of x. This is here h is the interval of difference. Let us substitute, instead of x, we substitute f of x plus h in the nth degree polynomial. Here a0 in place of x plus h, a1 x plus h plus a2 x plus h whole square, so on an into x plus h whole power n. Now the f of x term is a0 plus a1x plus a2x square, so on an x power n. Let us find the f of x by using these f of x plus h and f of x terms. Subtracting the terms, I just common the coefficients. This a0 minus a0 gets cancelled. The terms from a1 also, a1 only remains. a1 x power x plus h minus x, a2 into x plus h whole square minus x square, an into x plus h whole power n minus x power n. This is equal to x minus x gets cancelled, h remains here. Here also x square minus x square gets cancelled, 2x into h remains here, plus h square, a square plus 2x square plus 2xh plus h square. In this term, 2 into x into h remains, so on. Here look at this. For 2 is the coefficient, and 2 minus 1 x power 1, like that. Here n is the coefficient, 2 minus 1 1, like that, n minus 1 x power n minus 1, h, here h square, last term is h power n. Similarly, expanding and rearranging the powers of x, let us suppose the first term. Here there is no variable x, so we take this as b0, and this is b1 into x terms, x coefficient b1, so on x power n minus 1 term coefficients an. Here look here carefully, an into n into h. X power n minus 1 coefficient is an into n into h. This is the polynomial of x power n minus 1 degree. Now delta f of x is a polynomial of degree n minus 1. Similarly, let us find the second difference, that is delta square f of x, it will be a polynomial of degree n minus 1, similar to delta power 1 is polynomial of f of n minus 1 and delta square is a polynomial of n minus 2. Now, delta square f of x can be written as the first term C0 constant term C1 x coefficient C1. Similarly, x power n minus 2 term coefficient is an into n minus 1 h square. By using this, instead of n minus 1 we use n minus 2. Here n minus 1 in power term, before that, after that n here. Similarly, for this n into n minus 1 h square into x power n minus 2. Continuing this process n times, we get delta power n f of x is equal to the last term only remains, all the remaining terms gets cancelled since it is the difference an into n factorial into h power n. This x power 0 becomes 1. Since here an and n and h are constant, the delta power n f of x must be equal to a constant. Now, let us consider the n plus 1th term. Delta power n plus 1 f of x is equal to delta of delta power n f of x. We know the delta power n f of x is a constant. By substituting the delta power n f of x as an n factorial into h power n, the difference of a constant is 0. So, delta power n plus 1 of x is equal to 0. Hence, the theorem was proved. Thank you.